So the goal for today, I've lost my pointer, here it is to introduce folks to tandem mass spectra and how we might interpret them. And you know, I think that, well, in today's sort of world of mass spectrometry, there are countless computational tools that you're going to encounter to use that will help you analyze your data. But I still think it's really important that we kind of understand what underlies these computational tools and how one can interpret spectra manually, because I think it adds a lot to your understanding of the experiment and to the output you're getting, and to be critical of these tools that are very helpful. So just to give you a little bit of an idea of where I come from. So when I was a graduate student, it was in the late 90s, early 2000s, and I never collected enough data to really warrant any computational tool. It was all interpreted by hand because it was, you know, standard protein, digest it, see if we could see peptides. Pretty basic stuff. As a postdoc, I went and worked with Don Hunt at the University of Virginia. And Don's lab at the time, he was a pioneer of protein mass spectrometry, and they were doing LCM-SMS, and they were sequencing peptides from complex mixtures, and we used tools like sequest. And but there was always this back-end validation that involved printing spectra and manually checking them. And it was really incredible. You would see a stack of spectra this tall in Don's office, and he'd take them home every night and he would work on them. And they didn't publish papers unless someone had manually checked every spectrum. And you can't do that anymore because you can collect 100,000 spectra in an hour, so you just can't do it. That would be a whole career's worth. But it is useful to understand how to do it so that you can really know what you're generating. You can look at the quality of your data, you can assess it, and you can understand whether your tools are working the way you want them to. So I think there's a lot of value in that. So I learned how to do it a little bit as a postdoc, and I taught my early students how to do it. And we don't do it a lot anymore, but it can be useful. But as an educational thing, I think it's a really fun thing to try to understand them. So that's my background on this. I just wanted to review a little bit what you heard this morning from Professor Broadbelt. So there are a bunch of different ways to dissociate ions, and you heard about that. And collisions are the most common, as she talked about. There's reactions with electrons and photons, and today we're going to talk about, with the spectra, we're going to look at our electron transfer dissociation spectra, partially because it's what most of my experience is in, but also they're very straightforward to sequence if you get a good one. So, and we've picked good ones for you. So just to review, if you collide an ion with gases, you get internal energy that's vibrational, and then that thing can break apart, as we learned earlier today. ETD works a little bit differently, as you heard. Just to remind everyone, so we're going to start with a multiply protonated, in this case, peptides. These are the spectra we're going to be talking about today. And we're going to confine these peptide cations in this ion trap jointly with singly charged anions. And the anions, if we choose them correctly, will transfer an electron over to this multiply protonated peptide and then result in fragmentation. And to put that in the bigger context of what we're learning this week, and this is in a sort of proteomics-centric lens for right now, is we've learned a lot about analyzers. We've learned about how we have to ionize the sample to put in the analyzer. And this morning we learned a lot about how we dissociate these peaks or these peptides into spectra that we can then determine their identity. And just before lunch, we learned about how it's important to have separations. And the rest of this week, we're going to learn about, we're going to sort of build outward and cover all of these things. But just to give you an idea, so today we're talking about identification of spectra, but we're talking about it the old-fashioned way, and tomorrow you're going to hear about it in the modern way. And just to put everything in context, because we've seen all the different individual components, this is a hybrid mass spectrometer that happens to be an Orbitrap. So we've learned that ions can be generated out here by electrospray. They are transmitted. This is a mass filter. They can be collided or dissociated in here. They can be put in the ion trap, dissociated in there, either by collisions or with ETD reactions. And then the products can be analyzed here or back in the Orbitrap. And so just to quickly give you a perspective of how these things work, because we haven't put it all together just yet. We have peptides maybe eluting off of a chromatography column at a given moment in an LC separation. And these peaks then represent the masses of individual peptides ions, right? So, or populations of ions. So this blue one is the mass distribution of a population that has one sequence. And this green one's the one that has a different sequence. And so you can see all kind of peaks here, all kind of peptides eluting in that one fraction of a second. So then we have our quadrupole mass filter choose one of them to isolate. In this case, we chose this peak at 827 m/z, and not let any of the others through. So we're just letting this one through. And it goes down here, and we can fragment it. And then we can collect an MS2 scan, and we can look at the mass of all the pieces. Just in a moment, we're going to talk in detail about these pieces and how we can use them to sequence. But I just wanted to put this all together for you, from the LC, which is out here, to the ionization, to how these analyzers can work together to generate what we're going to be looking at. Any questions? Okay. So now this is what an LC chromatogram of peptide mixture might look like, and it looks awful gnarly because there's all kinds of peptides co-eluting. But at any given time, as we just saw, we have all of these individual peptide precursors that are eluting, and our mass spectrometer will then automatically work through and sample, isolate this one and sequence it. Isolate this one. When I say sequence, I mean do tandem mass spectrometry and collect a mass spectrum. And so it's this repeated process of isolating, fragmenting, collecting spectra, isolating another one, and that happens really fast. We saw some stats in the last lecture about the rate at which this can happen. It used to be 1 per second 20 years ago. Then it was 10. Now it's over 50, right, as these analyzers get faster. So this is this is kind of a dated slide, but here you can see in 1 second, this device collected 22 tandem mass spectra, and here they all are lined up. And the red ones are spectra that got matched to a sequence, and these ones didn't. So looks like 3 of the 22 didn't get sequenced, but the bulk of them did, and that all happened under a second, or about a second. And now these systems are twice as fast. You could probably do 40 in a second. So we're going to have, in this packet that I gave you, there are 11 tandem mass spectra. So that represents, about 200 milliseconds worth of data. And it'll probably take us 4 hours to do them all, and we're not going to do them all here. But just to give you an idea of the volume we're talking about, not to overwhelm you. All right, so we're going to get into this, and when we start to look at spectra, there's some things that you have to kind of have in your mind, and I want to remind everybody, we've heard about them yesterday, but we have to keep in mind that there are going to be isotopes in our analytes, our peptides in this case, and those isotopes will show up in our mass spectra, and we can use those isotopes to help us interpret the spectrum. So we define carbon-12 as having an exact mass of 12.000, and carbon-14 has slightly different than that, or you add 2 neutrons. And here we have a table of all the relevant atoms that would be in peptide mass spectra or elements, and exact masses for the different isotopes. And the one that we really are going to utilize the most here when we're looking at these spectra is carbon. And carbon is mostly carbon-12, almost 99%, but a little over 1% of it is carbon-13. So carbon-13 then, because a peptide has multiple carbons in it, if we have a population of peptides, there will be a subset that has one carbon-13. There'll be a subset that has two carbon-13s. And we can use that because we know the spacing in these isotopes is supposed to be exactly 1 or very close to 1. And so we can use that to determine the charge, right? Because we're measuring mass to charge. I'm going to show you an example in a moment. All right, the next thing you need to understand is that if these are peptide mass spectra, so that they are comprised of amino acids. So peptides are just polymers of amino acids. We don't know when we look at a spectra or spectrum how many amino acids are in the thing that we collected it from, but we can ballpark it based on the mass. So probably anywhere from 7 to 14 amino acids would make up most peptides that we're going to be sequencing when we do a trypsin digest. And the cool thing is that, so these amino acids have, for the most part, unique masses. With the exception of leucine and isoleucine, we can distinguish them by their mass. So we're going to use that as we look at these spectra. So in your handout, you'll find a chart that looks similar to this one right here. So why don't you go ahead and look for that and make sure we have it. It should be on the back page of the smaller handout. Does everybody have a handout? Do I need to get more of these out to you? I have more spares. So it's on the back page of the small handout. There's a table. This table is going to be very useful to you when we're looking at spectra because it has the amino acids, the one-letter codes, their compositions. I don't have the composition on your handout, but it has the nominal mass and the monoisotopic mass, and with many decimal places. The spectra we're going to be looking at come from an Orbitrap mass spectrometer, which has pretty good mass accuracy. So you will be able to use 2 or 3 decimal places if you want to help interpret these spectra. So we have that on the back page. So that's going to be pretty handy. All right, what's next? So let's start by thinking about charge, and resolution is important. This is kind of reinforcing some lessons we learned yesterday, but here is the example. So this is a peptide made up of lysine and alanine. And if we have a single proton or its monoprotonated version here, it'll be the mass of the thing plus a proton, and it has 1 charge. And when we take that mass measurement, we can, if we vary the resolution of the measurement, we can have, this is resolution of 1,000. And you can see this is the monoisotope, and this is the version that has 1 carbon-13, and this is the population that has 2 carbon-13s. If we turn up the resolution to 10,000, then we can very clearly distinguish these isotope distribution. And if we turn it up to 100,000, then it gets even much more separation. The spectra that we have are reasonably high resolution. I don't know what the setting was, but I think it's probably greater than 10 and less than 100, somewhere in there. So you'll be able to pull apart these isotopes and pretty easily see. But you can tell this is an isotopic distribution. And then if you put in this elemental formula into a calculator, it could predict exactly what this shape should be because you know how many carbons you have, and you can predict the probabilities of all the different isotopes. Okay, so now, so we're going to, when we interpret these, we're going to look at the precursor mass because we have to know what is the total mass of the thing that we've made fall apart. And I'll show you how to do that. And then we have to look at the tandem mass spectra, which shows us how the thing fell apart. And like I said, we're going to be working with ETD spectra today. And to refresh your memory from earlier this morning, I think the spectrum might have even shown up in there in that lecture. But basically, this is the sequence. And we dissociated this peptide by reacting it with this anion for 65 milliseconds. And this is the spectrum that results. There's a couple things I want you to note that Professor Broadbelt raised, but you may not have, that are going to be important, that you may not have noticed. But when we do an ETD reaction, this is the peak of the thing. So when we react this, it was a triply protonated peptide, and we had a big population of this. It would have been off scale here. And then we reacted it, and much of it reacted and either fell apart or got an electron but didn't fall apart. But we didn't react away all of the precursor. So some of it remains in our product, in our MS2 spectrum. So this is the remaining population of the thing I started with. It doesn't usually always, all of it, get knocked out, okay? Then we have all of these peaks in between here, and those are going to be the fragment ions, and we'll talk about C and Z in a moment. And those are going to be the things that help us determine the sequence. And then we see these peaks. You see these two sets here. So what happens is I started with something that has 3 charges and a fixed mass. I add an electron, so now I only have 2 charges because I took one away. If the thing doesn't fall apart, then its mass to charge value moves to here because it has 3. It's the total intact thing, but now it has 2 charges instead of 3, so its mass to charge value moves because charge changes, right? Because the mass was fixed. We call that the ET no D peak, right? And usually you get this little satellite peak to the left of that about 17 Daltons away. So if this is doubly charged, it'd be half of 17, and that's because you get some ammonia loss. Sometimes that really is a dissociation. It's just not a useful one, right? We cleaved ammonia off of that thing. Then if this thing gets an electron but doesn't fall apart, now the charge goes down by 1 again, and I have the same mass, but I only have 1 charge, and it moves out here. It should be this one. This is mislabeled. And now it's the M plus 3 plus 3H plus dot dot, right? Got 2 electrons, but didn't fall apart. And you'll probably see some of those in your spectra too. And then this is that minus 17 peak that we still have. All the rest of this stuff is most likely, they're informative fragments that broke the backbone somewhere. So what I'm going to have you do, when we start looking at these spectra, the first thing we're going to do is we're going to calculate the mass of the thing, and then we're going to annotate our spectra with these precursor and these ET no D peaks so that we don't confuse them for fragments that were actually going to be useful. Because we can calculate these out and we can label them and we can get them out of the way, and then we don't confuse them as sequence ions. All right. Now, we also learned this morning about how a peptide backbone can break. If it breaks at the amide linkage here, you get what's called a BY pair. And that usually results from collisional or vibrational activation. If you break it to this bond here, this carbon-carbon bond, then you form what's called an AX pair. Usually happens with higher energy dissociation like UVPD, something like that. And then if we cleave the NC alpha bond here, we get a C and Z. Now ETD will primarily make C's and Z's. You will sometimes see a Y and you'll sometimes see an A. But you start by making C's and Z's, and then this Z can unravel to become a Y. But that's not too frequent. So we're primarily going to be looking for C's and Z's in our spectra. So that would be like this. And one thing I want you to note here, and I have this board so I can write. So if you were to cleave, oopsie, sorry, wrong way. If you were to cleave this bond as shown here, right? So then if there's a charge on both ends, so if this has a charge and this has a charge, then there's a relationship between C1 and Z3. Does anybody know what the relationship is? They have they both, they resulted from the cleavage of that one NC alpha bond. So a relationship that we could imagine is that the mass that I measure of C1 plus the mass of Z3 should equal something or be related to something. What do you think it is? Yes, we can relate it to the mass of the M plus H. So it turns out that a CZ relationship like this can be equal to the M plus H plus 2. And the 2 comes from the protons. We can talk about that later. But this is we'll go over this. I've got it in your handouts. But this is called a complementary pair. Those two ions are complementary because they arose from the fragmentation of that one bond. And if you put them together, you get the total mass, right? So those are called a complementary pair. Sometimes you'll read about them as called golden pairs. Has anybody ever heard the term golden pair? I date myself with this literature. Complementary ions, complementary pair, golden pair. All those can apply. Those are special, and you can use that relationship to your advantage. So we'll just walk through this one, and then we will get right at it. So here's an example tandem mass spectrum by ETD, and I've got all these masses labeled. The precursor was a +3 at mass to charge 277. And what we can do here is if we find a peak like this C1, so the other thing I should say is that the C ions always contain the N termini of the peptide, and the Z ions always contain the C termini, right? So you're working from one end or the other when you do this. So if I find a C ion, that one, then I can say, based on the mass of that, and I'm going to show you how to calculate this in a moment, that because that mass is 146, I know that's the first C ion, and it must have lysine, because it corresponds to the mass of lysine, and we'll show you how to calculate that. So then all I have to do is find the space between this peak and one of these other peaks that adds up to the residue mass of one of the 20 amino acids. That's where this comes in handy, right? So you can just look on this and say, well, the distance between here and here is 71. And I look on my chart, say, nominal mass 71. Alanine. Alanine is 71. So if it was an alanine in that spot, then that would give me rise to this peak. So then we can say the next residue is alanine. And then we look again and we say, oh, look, there's another alanine. And we walk down the sequence, reading off 3 alanines in a row. And then we go and say the next spacing is 128. That corresponds to lysine. So the next residue in the sequence must be lysine. And then we find that there's 3 more alanines in the sequence. Bang, bang, bang. And then based on the mass, the difference between this and the total mass, I can get to the end with a lysine. Okay, and now that's reading the sequence forward with the ions from the N termini, the C ions. I can read the sequence backwards with the ones from the C terminus. All these, the Z ions, right? So these ones will be reversed. So I'm going to start here, and I'll have a lysine, alanine, 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 lysine, alanine, 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 lysine. Okay? So we can read the sequence forward or reverse depending on whether we're looking at C or Z ions. And if we can find a C ion, but if we find, say, 202, we can calculate the next C ion, the complement to that, because we can relate that by mass, and we can go hunting for it. I'll show you how to do that too. So we can use all these tricks to get to the sequence. Yes?
Why did you skip the one peak?
Right. That peak right there is our ET no D peak.
Okay.
Yep. So we know, and we can calculate that. This turns out to be the same. This turns out to be the same peptide that I showed you earlier. Not that one. Oh, sorry. It's the ET no D peak. And I'll show you how to calculate that. So that's going to be easy to know that it's not the right thing. Yep.
I have another quick question.
Yes.
I apologize if I missed it. Is there a reason there is a 15 mass difference between C and Z? Is that characteristic to this peptide or something?
Oh, right here. Yeah, that's coincidence. It depends on what this residue is and what that residue is. And I don't have it here, but I can go over it if you want. So there's the amino acid residue mass, and then there's like the stuff that makes up the C term. And then there's this, if you put that same amino acid on the end term, there's different stuff that makes that up. So that's why they're not the same number.
Will the
Okay.
difference of 15 carry over through any specific?
Not necessarily, no.
But it does here.
Yeah.
But the sequence is symmetric.
It's a weird sequence. Probably not the best example. Yeah. Any other questions? Yes.
So again, after the first amino acid, how you like calculate, I'm still not clear. There's like that first offset for the lysine, how the mass is like.
Why it's not 128?
Right.
Yeah. Yeah. Let me. I can explain that. Let's see what I have next. I don't know if I have it set up. Okay. So let's just walk through that right here. So. The numbers that you have in this table come from what we call the residue mass. Okay? So these are the numbers of the masses for each of the 20 residues. And we define the residue mass having, this nitrogen, the alpha carbon, and this carbon, and the carbonyl, and the R group, and an NH. So that's what we call the residue mass. Now to get to, this will lead nicely into getting started. Hold on a second here. So to get to the Z1 mass, where's my writing? Oh, I ditched it over there. Sorry. So, can't touch the screen. Okay, so Z1, sorry, got to get used to this. If I had, let's see here. I borrowed this from another structure, but basically, we have, this is the C terminus here, and this is the R group here. So now we have to relate, so that would be the structure of this. Sorry, it's a little not clear. So this is the R group, and this is our C terminus. And so what we have to do is we have to relate the residue mass, this, and get it in terms of the C term. And so you basically just say, well, I have this, NH, we lost the NH in this case. R, that's the residue mass. But I've added a proton, an OH group because I'm on the C terminus, and I've lost the NH group from the residue mass, so it's that. Okay, so this is the residue mass. It's this formula. And then if I just work these out in terms of numbers, I get 3. So the first Z ion, you can always calculate it by just saying it's the residue mass of the amino acid on the C term plus 3. And you get the 3 because of the kind of currency change we have to do to get from the C term to the residue mass. So this might be a little confusing right now, but let's just do a few and you'll see how this plays out. So the other thing to remember is that we're using trypsin as our enzyme. I've lost my pointer. And so because we use trypsin, we know that there's a lysine or arginine on every C term. So if the C terminal residue is a lysine, the Z ion, this first Z ion will be 128 plus 3, 131. If the C terminal residue is an arginine, it's going to be one or the other. Then it'll be 159 because it's 156 plus 3, 159. Okay? You don't have to write that down. I think I've got it in your notes, so we'll have that. So let's go ahead and let's do the first one together. We're going to do 2 together, and I think you'll see how this all plays out, and we can work through your questions. But let's start with problem number 1. Who needs pencils or calculators? Anybody? Which do you need? You need both. All right, so maybe Evgenia, could you distribute these as needed? If you need a calculator or a pen, Evgenia, raise your hand and she'll get you set up. So bring out problem number 1. Let's start with this one. And we're going to work through this, and I think it seems probably super complicated right now, but it's not too bad. So the first thing we have to do is we're going to need to calculate charge. Okay? Calculate charge. So on this one, it's rather straightforward. Well, they're all rather straightforward. So we take this mass to charge and this one. And you can see that this is an isotope distribution of the precursor. So this is the thing that showed up in our MS1 scan. And you can see the C13 peak right there. And so what we do, and you can follow along on this sheet right here. I've got the numbers for this exact problem. So basically, we take this peak 302.826, and we subtract the monoisotope peak 302.492. And when you do that, you'll get 0.334, or basically 0.3 MZ units. Okay? And now we know the mass that those isotopes should be apart. The mass is 1 Dalton because it's a carbon, right? It's a carbon-13. It's a neutron. So then we can calculate the charge by saying that charge then is equal to that mass, 1, divided by 0.334, which is 3. So that is a triply charged precursor. Any questions about that? You'll get so good at this that you'll just look at this and you'll say, oh, it's 0.3 triply charged. Or if it's 0.5, it's a doubly charged, right? If it's 0.25, it's 4, right? So it's integer units. It's going to be 1, 2, 3, 4, and you probably won't get more than 4 on peptides from Triptych Digest. So that's what you're looking for. So we got to know the charge. Now we know the charge, we can get back to mass, right? With that number and the charge, I can tell you the mass of this peptide. So that's the second thing we're going to do. Okay, so number 2. So this is 1, calculate charge. 2, calculate the M plus H plus. Okay, so this is also pretty straightforward because we know that, so the general way to do this is that the M plus H plus, I'm just kind of rewriting the notes that you've already got there, will be equal to the precursor mass to charge value times the charge minus the charge minus 1. Sorry, I'm having troubles with this pen. Times 1.008. Sorry. Okay, so this seems tricky, but it's not. The 1.008 comes from the mass of hydrogen. So basically, our thing has 3 protons on it. It's triply charged, and we want to calculate the mass of the thing that has only 1. So we take the mass we start with, the precursor mass, 302. We multiply it by 3. That'll give us the mass of the thing I measured, but I want to know the mass of the thing with only 1 proton, not 3. So then I have to take away 2 protons worth of mass to give me the M plus H plus. So I'll just write that out, and then if you're confused about that, raise your hand and we'll talk it through. So in this case, you got it in your notes there. It's 302.492 times 3 minus 2 times 1.008. And that gets us to 905.46. It's the M plus H plus. M plus H plus. Okay. Any questions about how to do that? Yes.
Say in the original formula, Z minus 1 should have another bracket. So you are using 3 minus 1 bracket multiplied by 1.08.
I need another bracket.
So Z minus 1 multiplied by 1.008, right?
Yep.
So you need another bracket for Z minus 1.
Sure.
Otherwise you will
I want it to be 2. We're going to do 2 times 1.08. So yes, let's do that. There you go. OK. All right, so we've got that mask. Write that number down because we're going to use it in the next step. So now turn to the next page. That's a tandem mass spectrum. And now we're going to have to figure this thing out. So what we learned from the last example is we don't want to be confused by the ET node D peaks and the precursor that's remaining peak. So let's calculate one. We're going to calculate charge reduced, what'd you say, ET node D plus annotate. So we know that the thing we started with was this one, right? And that is the M plus, we calculated 3 charges. So it's that. Okay. And let's see here. And now we know that the 907 peak here, well, I can just work out this. We'll do it the longhand way. So if we want to calculate the M plus 3H plus dot dot, that's the doubly charge reduced precursor. That's pretty easy. That's just going to be the M plus 3H 3 plus times 3 equals 907.476. And it's this peak right here. Sorry, M plus 3H plus dot dot. Okay. So we got that one. And then the this one, so now it could get 1 electron but not fall apart. So then we just do this. M plus 3H 3 plus times 3 divide 2 because it's doubly charged. And that'll get us 453.738. That's this one right here. M plus 3H 2 plus dot. So now we know that those 3 peaks are not C and Z's, and we won't confuse ourselves by trying to use them as a sequencing ion. Okay? All right, calculate and annotate. These are all going to be pretty straightforward. These are all triply charged precursors, so you can use the same strategy. And then once you get the hang of it, it doesn't matter if it's doubly, quadruply, it'll be pretty straightforward for you. If it's quadruply charged, you'll have 3 charge-reduced peaks, right? Because you have the 3 different possible charge states. And if it's doubly charged, you only have the 1. Second step. I think the easiest thing to do next is to look for Z1. And the reason that I usually start by looking for Z1 is because we're using trypsin, and there's always going to be a lysine or arginine on the C term. So it's pretty straightforward. Plus, lysine and arginine are pretty basic, so they're likely to be observed as an ion, right? Because when you get something very small like a Z1 or a C1, they have to be protonated for us to see them. And the arginine or lysine will carry charge well. So we just talked about how to find those. And so let's see. I'll write some notes in here for you. So remember, Z1 is equal to the residue mass plus 3. And we only have 2 options. If K, then it's 129 plus 3 131. If R, it's 156 plus 3, or 159. And this one's right there, 159. That will be Z1. Okay? So now the way that I like to annotate these spectra is, and to keep track of all this stuff, is to write, if I've figured out the first residue on the C-terminal side, I write it right up here on the top. And then I write the mass for that as a Z-ion right underneath it, 159. And then we can draw a line under it if I've observed it in my spectrum. And this will help you to build out that sequence and to keep track of things. So far, we've done 3 or 4 things, right? We've calculated the charge state of the precursor. We use isotopes to do that. We used that charge state to determine the M plus H plus. We're going to use that M plus H plus in a moment. So it may be a little mysterious why I had to do that, but we're going to use it. Then we used the charge state and the precursor mass to calculate all of the ET node D peaks and to annotate those things away so we don't get confused. And that's the exact same procedure you're going to use for all of the problems and any manual sequencing that you ever want to do. Hopefully you do it after today. And then we're going to start looking for Z-ions because I think that's usually the most straightforward thing to do. And you've only got 2 options, 131 or 159. And we found Z1. So we can say with pretty good confidence that the first residue on the C-terminal side of this particular peptide is an arginine. Any questions about what we've done? Okay, now the fun begins. We have a couple of ways to go about this at this point. And I think what we'll do is I'll teach you one. So if you go to this, it's not numbered. I'm sorry I didn't number it, but there's a page called Calculate C and Z Ions. That's the step we're on right now. And there's lots of different ways to do this. There's no one way. It's sort of like doing the Wordle if any of you do it. There's lots of strategies you can use. And this is a puzzle just like any other puzzle. But these are some key things, this top 4 list here of tools that you can use to go after this problem. Or basically, there's 5 things here. And then I've got some notes that I think are helpful. Let's just start with some of these notes. So, and I should have made a blank page, but I'll just rewrite it. So the mass tolerance that we're going to be looking for here is plus or minus 0.1. 0.01, sorry. So when we start looking for the next steps, we should expect that the correct path, the solution to this, the masses should work out to be better than plus or minus 0.01. If you find a step, let's say you think 236 is the next ion in this series, and it matches perfectly to tryptophan, I'm just making this up. If it's not within 0.01, it's probably not a legitimate path to the solution. So that's kind of, just keep that in mind. And this number that you use for that just depends on the mass analyzer you have and the confidence you have in your data. When I started doing this 20 years ago, it was plus or minus 1 or thereabouts, right? So like you can imagine lots of possible answers when it's that big. But this is pretty tight. That makes it a lot easier. So just keep that in mind. The next step should be there. So let's just do, I want to show you one thing before we just go looking for the next Z-ion. And that is, and let me just erase this. You have that in your notes anyway. How we can calculate the complementary Z-ion, or pardon me, C. Because I think that's a useful double check as you go. So if we are correct about our annotation of arginine on the C-terminus, if that's the correct answer, then we should expect to find a C-ion that is present that fits with this mass of 159 because of the complementary pair rule that I told you about. So there's a shortcut way to figure these out, and I've got it noted here, but a CZ pair should be equal to the M plus H plus 2. Okay, so then that means that we should be able to calculate this one by taking the, can anybody remember what is the total M plus H plus of this one? This is 905, yes. Okay, so 905 plus 2 equals 159 plus C, I'll call it N. So 907 minus 159 should be equal to the biggest C ion. And I think that will come out to be, is it 748? Does anybody crunch that for me? Yes. 748. Okay, so see how I wrote 748 up there? It's not very legible, I'm sorry, but it says 748. And this is where we're going to put a letter right here, right, once we figure it out. But if we're right, 748 will be in the spectrum, and it's right there. So that gives us confidence that we picked that Z1 correctly. So let me annotate this for you. We don't know what the next letter is, but we know, I'll just fix this so it's clear. 748, and you can calculate the exact mass because you have these numbers exactly. And I think what you'll find is it works out to this number right here. And so we'll annotate this as a C ion. What number C ion is it? Who knows? Anybody know? We don't know because we don't know how many amino acids are in this sequence. And we don't, so what we'll just do is I'll just call it Cn, C sub n, and then the next one will be C sub n minus 1. So we'll just call it Cn. Because we have no idea how many amino acids yet are in our sequence. So we don't know. But because we're on the C term, we know that's Z1 at 159. Okay, so now let's go to looking for Z2, the second Z ion. So our options are, it looks like here, here, here. These are kind of low, maybe that one. Can anybody go from here to here, or to here, or to here, or to here in allowed increment? And the allowed increments are on this list to plus or minus 0.01. Can anybody find an amino acid that matches those steps to the mass accuracy that we think we should have? 306. If you go to 306, I'm told you get an allowable step. What was the step? 147. Okay, so then we would put 306 here. So that next residue is F. And we write down 306, and we underline it. We can underscore this and call it Z2. All right, now we can calculate Cn minus 1 by saying it's 907 minus 306. And if you do that, you'll come up with 601. Oh, look, we've got 601 right here. That would be Cn minus 1. So then the complementary C ion is indeed present. Feel good about that. That means you're probably right. Now you can see, go ahead, Corinne.
Just real quick on that one, it was 748 minus 147, just phenylalanine, not 302.
Pardon me?
Sorry, when you were saying it out loud, you had said it would be calculate the C ion would be 748 minus 302, but you just calculate the difference in the one residue to get to 601 for that step.
You could do that, or you could take the 306 from 907, right?
Yeah. I guess so.
Yeah. Maybe what I said and what I wrote were not the same. I'm sorry. Sorry about that. So good, we got Z2. So you can start to appreciate, I think, how the quality of your MS2 can really impact the quality of your life. If a lot of these ions aren't present, it's harder to do, right? So let's keep working through this one, and we'll get there. So we've got FR. I'm going to get rid of this to clean this up. Who's found Z3? Anybody? Yes, tell me. 405. Thank you. And that is a valine. Is that what you got? V. 405. Excellent. And now we'll calculate the complementary C. And I've calculated that at 502. If I've done it wrong, please let me know, but I think that should be it, 502. You're right, Corinne. That's another way to do it. You just, from the 601, subtract the residue mass, and you'll get to the number. You could have done this, right? Subtract 405 and gotten Cn minus 2. Or you could have just said 601 minus 99 and gotten to the same number. I'm sorry, yeah, and gotten the same number, correct? So you can do it however makes sense to you. All right, we're at Z3, 405, Z4. Who's found it? Go. That's what I have. Okay, very good. Here is Z4. And that is going to be histidine. 542. And we can go ahead and calculate the complementary C ion, which will be at 365. Cn minus 3. We're getting close to the end. We've only got 365 Daltons to work with. You can't fit too many amino acids in that mass. So we're probably talking 2 or 3 amino acids to go. And we have 365, sorry, let me annotate that. Okay, so we'll just keep working on the Z series since it's working so well. Who knows the next Z ion? You've got a few options. Yes? 671. That's what I have, 671, good job. Z5. Okay, so that would give us E, 671. And we calculate the next C ion to be 236 based on those numbers, 236. And we do see it, Cn minus 4. All right, can we find another Z? You could choose, these guys are pretty low. There's this one, this one, this one. Anything work? 742, yes. That is going to be Z6. And that is alanine. It's a small one. 742. And we can calculate now the complementary C. Would be the mass of alanine subtract 236, or 907 minus 742, and that will be 165 right here. And we have it. Okay. So now we have we're kind of up against the end of this thing. And it could be that that 165, that C ion at 165 is the first C ion. But I haven't yet told you how to calculate the mass of the first C ion, but that's going to be on this little cheat sheet right here. The mass, and we'll just check and see if it is. C1 is equal to residue mass plus 18. And so now we can just take 165, subtract 18, and see if it's a residue mass. Does that work out? Yes, it does. It's F. Wow, we did it. So that is the sequence of this peptide. And you know, if you're uncertain of your answer, you could take that sequence and you could calculate the total mass of it, but it'll work out to the M plus H, I guarantee you, because we've done that. And the cool thing is that we have annotated pretty much all of the major peaks in this spectrum. We've explained them. These guys here, this minus 17 is a neutral loss, and the same thing here, so that's not worrisome. And sometimes you get bigger neutral losses from the, so I suspect that's what these guys are. But pretty much everything else is explained. There's some low-level stuff here. We don't know what it is. Maybe it's an explainable ion. But we've accounted for pretty much all the major peaks in this spectrum, and everything fits really well. So this is the answer. How'd it feel? You did it. How many of you have done this before? A couple people. Good. So let's do another one together. One thing I forgot to point out was that when you look at these spectra, I'll show you on the next one that's not all complicated. But so here's problem 2. And we won't start here, but you see how up on top there's this little X5 here, there's an X10, there's an X5. I forgot to point that out on the last spectrum, but that is simply a denotion to you that this whole region of the mass spectrum has been inflated by a factor of 5 relative to the total intensity. So I think you just have to be aware that this 159 right here, while it seems big, relative to some other stuff, it's been blown up by 5, factor of 5, and that doesn't mean that it's not real. It just means that it's not. It's like objects in your mirror. They're closer or something than you think. Here's a 10, and that one's blown up by 10, and a 5. So just as you look at them, I want you to understand what that means. So let's go ahead and we'll do number 2 together, and then once we've done number 2 together, I would like you all to work through some of the other examples, and we've got the TAs, and I'll be working around, and we'll just help you. But let's just go through this one first. So problem 2, we've got, we're going to calculate charge. And we can do that 359.517, subtract 359.183. That'll work out to 0.333. And so it's the same deal. Charge then equals 3. I shortcutted some stuff there, but and I'm happy to slow down if you want, but it's basically the same ideas that we had before. It's 1 Dalton divided by 0.33 will give us the charge of 3. So from that, we can do the M plus H plus as 359.183 times 3 minus 2 times 1.008. And I don't know if I wrote that down. Can someone tell me what that works out to be? $1075.532. Ah, thank you. Okay. We got it. All right. We've got the M plus H. And now we're going to start looking at the spectrum. And I'll bet everybody has already found Z1. It's right here. Oh, I got ahead of myself. I'm so sorry. I got excited. We should annotate these other things. The precursor was 359. So this one is the M plus 3H, 3 plus. And this must be the doubly charge reduced ET node D peak. And then we can just divide that by 2. 1077 should be 5. I'm thinking it's this one. Where's our plus 2 ET node D peak? Does anybody know that mass? It's this one. M plus 3H plus dot. Okay, there. We didn't get ahead of ourselves. We labeled those things so we won't get confused. And we found C1. We need to calculate C1, the biggest C ion, we'll call it Cn. And we can remember how to do that. I have that formula for you, that the largest C ion is our M plus H. M plus H minus, we're going to use the pairs, sorry. 1075.533 plus 2 is equal to the biggest C, I'll call it Cn, plus 159. And so now we can just work that out, and we will get, I believe, 918.452. That's this one, Cn, 918. Okay. Who's found Z2? Yes, Z2. What's the residue? Thank you. Tyrosine, 322. Who's got the complementary C? What's that one? Cn minus 1. You can calculate that from the 322. 755. Excellent. You guys are pros. Cn minus 1, 755. Perfect. That's good. We're off to a great start. Tyrosine, arginine. We have complementary fragments explaining both of those. What is Z3? Z3? You got a few choices. Okay, we'll mark it up. Z3. That would be aspartic acid. 437. Excellent. Complementary C. $640.3. Cn minus 2. We'll put it up here. Boom. Who's got the next Z? It's kind of a mess up there because you've got all this stuff from around this guy, but can anybody find a nice clean jump? Yes. 527. You like that one?
Sorry, 508, 508, 71. Alanine.
5. Which one do you got? 508?
766.
So if I go from here to here, what's that difference?
Alanine, 71.
And does it fit 0.01? Oops, sorry. So it needs to be there. So alanine's possible, but I think your tolerance is probably a little outside of 0.01. We'll keep it on hold. Does anybody find a different solution that matches within 0.01? I hear 550, this one. If that one worked out, we would be isoleucine or leucine, and does it fit within 0.01? Yes, people have nodded. Okay, so this is an excellent example of what to do. So when we were working on these problems, last week, my group, we did a pre-session, and one of us made that jump to 508 with alanine. Was it Noah? Noah, what did I tell you when you found that?
You can keep trying that sequence, and it's probably going to fail eventually.
I said, if you think it's the right answer, keep working it. I bet you'll go off the tracks pretty soon. And what happened?
2 residues later, it didn't work.
So I think I'm glad this came up because sometimes there can be multiple choices and you don't know what is the right answer. And this is a case like that. And we can use this mass accuracy to help guide us to the right answer, but sometimes they both might be within the window. And what you do in those cases is you just kind of play it out and you look and you say, okay, well, if that's alanine, can I find a complementary C? And I don't remember, did you find a complementary C in that case?
Yes.
You did, so that might make you feel like you're on track, but then eventually it went off the rails, right? It didn't work out. So then in that case, you'd go back and you'd say, okay, well, I don't know if I made the right step. Is there another option? You say, oh, there's 550, and then you'd work that and you'd get there. So, to do these well by hand, it takes a lot of intuition and practice, and you'll learn it. And I don't imagine any of you will probably ever have the need to do that. But if you do, that's what you would do. And in this case, alanine is tempting, but there's a slightly better solution, which turns out to be the correct answer, and that's this one right here at 550, Z4. So we'll write that in, and we'll go, I'm just going to write I, because it could be I or L. You don't know the difference. We'll use the genome sequence to tell us the right answer, so it doesn't really matter. Okay, that is a nice, that is a nice example of what could happen. So we'll get rid of that. And the complementary C on that one will be this peak here at 527, Cn minus 3. 527. Okay. So now going forward with the Z series from 550, is there any option? Yep, perfect, 687. That's the one I had too. They don't often get that close, but they can, and that's when you just have to kind of like be prepared to backtrack if things don't work out. That would give us the next residue is histidine, 687. And the complement to that, did anybody calculate the C complement? 390. Thank you. 390, and it is here. Cn minus 4. Good. And I need another Z ion. $815 is in a desert out here. Bless you. It turns out that works out pretty well for leucine, isoleucine, leucine 815. And the complement to that will be 262. Cn minus 5. 262. Okay. And Wait, I'm off the rails here. I'm sorry, I missed a residue. I went too fast. This is Q. And this one is L. I'm sorry. 928, right here. Z7. Okay, and then if we take the mass of 113 from 262, we get 149 right here. And look at it's a little peak right here. That's going to be our first C ion, 149. And if you go to your cheat sheet here, C1 is residue mass plus 18. So we'll just take 149 minus 18, and that'll give us 131. What is that? Thank you, methionine. Boom, we did 2. And again, we just want to look over at the end and make sure that we've explained most of the peaks, and we indeed have. Every one of our backbone bonds is cleaved, and we found complement. We found all the C and Z series. The other thing I forgot to point out is that there may be some doubly charged peaks in here, but most of them are singly charged, and so you don't really have to worry about charge states. But if you're looking at B and Y type spectra or CAD type spectra, you're likely to find multiply charged things. In the ETD, you'll see less of that, but it can happen. Yes?
I'm sorry, I might have missed something, but I don't, how can you label between L and I if they both have
Oh.
the same 113?
Yeah, question is, how do I know the difference between L and I? Because they're both 113, I don't. So the actual sequence is an L there and an I there. If I'm manually sequencing, I'll just write one or the other. And then later, you can use the genomic sequence to tell you what the right answer is. Yeah, if you don't have genomic sequence, you'll never do better than I or L because you can't tell the difference. I mean, there are ways, but it's complicated and it rarely works. So the genome will tell us the answer. So you can write down whichever one you want. Okay, any other questions on this one? All right, so next, why don't you guys work together at your tables and see how many you can get through. When you get an answer, let's take a picture together and we'll show it off and you can post it on Twitter. All right, well, let's take a pause and jointly go over problem number 3. So if you want to wrap up and pull out your problem number 3, we'll go over it together and address any questions. So I think some of the feedback that I've gotten is that some people may be still a little bit confused about mass to charge and calculating the ET no D peaks and their masses. So I think we should just, I know many of you got this, but I think there's a little bit of confusion here. So if we look at the first page of problem 3, we can see our monoisotopic peak right here at 328.179, sorry. And then this is the 1C13 peak, right? It's got a 1C13 atom. So the way we figure out charge is we take 328.513, subtract 328.179, and find that that's about 0.33. And because we know that the mass that's driving this difference equals 1 for the neutron and the carbon-13 difference, we can divide 1 by 0.33, and we can get charge equal 3. So we know the charge state is 3. And that means that this is an M. The M stands for the peptide, right? The peptide M, or mass. So it's that mass of that peptide plus 3H. And each proton gives me a charge, 3 plus. So the thing that we started with was a triply protonated peptide. Any questions about that and how we did that? Okay, good. Now to get so for solving these things, we'd love to calculate the M plus H plus singly charged. And so to do that, we're just going to, now that we know charge is equal to 3, we know that 328.179 times the charge will give us the mass. Right, I'll annotate this. I should have done that. So it's mass to charge times 3, which is in units of charge. So that cancels out, right? And we're going to have a mass value for that thing of 3 times 328.179. And I don't have a calculator in front of me, but does anybody know what that is? 900 and, go ahead.
984.
Thank you, 984. But then we have to subtract the 2 protons from it because it has 3 on there, right? And we got to get rid of 2. So we're going to subtract 2 times 1.008, which is the exact mass of the protons. And so we'll get a number around 982. Is that right? Any confusion there? We're good? Excellent. Okay, so now we go to our spectrum. This is number 3. We started with 328. So this peak right here is the M plus 3H 3 plus. That's the thing we started with. And just remember, sometimes in collision-activated spectra, that'll mostly be gone. You won't really see much remnant precursor. In ETD or ECD, probably even some of the photoactivation methods, usually you get a little residual precursor. So it's still in the spectrum for the MS2. It's just not gone. It's like you have a little bit of it that survived. So we annotate that. And then we need to figure out so we know, let me just kind of write it out this way, that this thing gets an electron, and sometimes you get C plus C fragments. But sometimes you get ET no D. And ET no D would be that, right? Capture the electron, you don't fall apart. And we don't want that, but that M plus 3H 2 plus is going to be in our spectrum. And likewise, this thing can get an electron, and it could then finally make our C and Zs, or it could make this. Gets another electron and doesn't fall apart, and so we have that. So the next step is the annotation part. We've annotated this in our spectrum so we don't get confused, but now we need to annotate this and this. So we just need to calculate the masses for this. This one's easy because it's just 328.1789 times 3. And we don't even have to subtract the protons because they're still there, right? We didn't get rid of them. They just got electrons, and we can't measure the mass of electron well enough, so we don't have to worry about the mass of the electron. But the protons are still there, so the plus 1 is just the thing times 3. And we did that earlier. That was 984. Whoops. Oh, shit. Okay. This one. M plus 3H plus dot dot. So that's easy. Okay, how do we calculate the mass of this one? Well, it's doubly charged, so the easiest way to do it is to take this number, 984, and divide it by 2, because it's got 2 charges on it. So it's half the value because the charge goes by. So if I divide it by 2, then because its mass is 984, number of charges 2, mass to charge will be 984 over 2. And that is going to be this peak right here. It's not annotated for us nice and clean, but it's at what's this guy right here? M plus 3H 2 plus dot. Okay. Everybody with me on that? So that could be a little bit tricky, and I think that's maybe among the hardest concepts that you had to pick up here, because I think it's relatively straightforward to understand the residues that we're adding, right? And we can calculate all that. The other thing that came up in some of the questions and talking to some of you is that there's these peaks here, and there's these peaks here. And if you go through the sequencing, as many of you have, maybe all of you have, you'll notice they don't map to any CNZ ions, yet they're there. And I told you you should worry about every fragment and you should try to explain them all, but yet you can't, and I didn't tell you how to. So it turns out, and I was trying to simplify your life by withholding too much information, but it turns out that when you do MS2 on peptides, whether you're doing ETD or collisional activation, and Professor Brabell talked about this a little bit, you can get what's called neutral losses. So you can take the mass I started with, and neutral mass can fall off without taking a charge, and then that mass of the thing I started with is less by whatever amount fell off, and that's called a neutral loss. Now they're different. Collisional activation neutral losses and ETD neutral losses are somewhat different because each is them a different method. But it turns out that, that these peaks correspond to known neutral losses that happen with ETD. And so this particular spectrum just happens to have a lot of them in it, so it's more prominent and it was more noticeable. But let me just pull up for you real quick, if I can. That's weird. I don't know how to go. Oh, keep. Oops. So there's a. Where do we find Google? Why is no Google? Google. If we just search for ETD sidechain losses. Here's a paper we published, 10 years ago. Okay. Seems like yesterday. On these neutral losses. And here they are. So we did an analysis of when you do ETD, what neutral losses do you get? And here you can see that it's a start of a table. And what you'll notice here is that we have all these neutral losses in Dalton. So so if you're looking at the singly charged cluster, you could get all of these losses from the M plus 3H plus ... The most prominent ones are 60, 17, but what you can see is they're amino acid dependent. So these neutral losses typically come from the side chain of an amino acid. And so if you have an arginine in the sequence, these are the ones that you might see. If you have a histidine, these are the ones that you might see. And so it turns out there's a lot of them, and then you can get combinatorial effects if you have multiple neutral losses. So it can get a little bit messy. They go up to about 100 Daltons. And I've got the compositions here. And so this column shows us, at the time we were thinking you could use these in a search algorithm so it could help you know what you had. But this tells you the sensitivity and specificity of these. So if you get an 82.05 loss, then you can be 100% certain you have a histidine, or at least that's close to certain. And if you have a 59, you can be pretty sure that you've got an arginine. And I guess that means that about half of the arginine-containing peptide should show that neutral loss. So that's what you're seeing there. And this one, they're pretty prominent. So you probably noticed them and you were confused on what they meant and why they were there. Does that help you understand them? Let's go back to those spectra and just take another look at them with that in mind. So you see them here, and I didn't work out all these masses, but we have an arginine in the sequence and we have a histidine, so it could be a combination. That's probably why they're so prominent. But you'll notice that they're here as well, and that they're probably they're going to show up with half the spacing because these are doubly charged, so it's going to be half the distance in MZ units, but it's the same thing. Anybody with me on that? Okay, let's get into the sequencing of this one. And my pen has turned red. I don't know why. We'll just go with it. Who would like to? we chose this as a 159, right? So that's our Z1. We're trained there. And the complementary C would be 825. I have these all worked out, 825, so that's CN. What's the next Z? 230, that's what I have, Z2. That's alanine, 230. The complementary C, if you deduct out the alanine mass from 825, is 754. And it's this one, CN minus 1. And that gets us to what is Z3? 343. Yes, it's right here. Z3. And that would be isoleucine. You can do it however you want. Just to be, how about I'll just do this? Many of you asked, how do we know? We don't. What we'll do is you could use the genomic sequence to tell you the answer, because you can just put in the whole sequence and it'll tell us what the right answer is. But for now, we don't know the difference. There are some reports that in ETD spectra, you can sometimes get a side chain loss of leucine or isoleucine, and therefore you could determine which ones. But it turns out it's such a non-problem that we don't really, it's not that big a deal. So we haven't really pushed on that. 343, and then the corresponding C to that would be 641, I think. CN minus 2. 641, okay. All right, then we're going to go from 343 to, yes, it's kind of in this mess. Sorry. 480, Z4. That is histidine, 480, and then the complementary C would be 504, right here. CN minus 3, got it. And after 480, thank you, Z5. And that is serine. 5, 6, 7. Complementary ion is 417, which is here. CN minus 4. And then we go from 567 to,
681.
thank you, C6N. 681. Complement would be the 417 subtract the mass of N, which is 303. And now we just probably go to 780. It's not much left. Z7. And that would be V. 780. And the complement is 204. Got it. CN minus 5. And now we can use our trick to figure out the smallest C ion is residue mass plus 18. So we take 204 minus 18 and we get W. Okay, is that what you all got? You are now bona fide mass spectrometrists. Congratulations, that's fantastic. So, okay, give yourself a round of applause. You did it.